The rest of Chapter 7 will delve more into types of chemical reactions, and those will be classified as either acid-base reactions or redox reactions. There's a bunch of different ways of classifying chemical reactions. We will talk about precipitation reactions, double replacement reactions. You probably have heard of those. Acid-base reactions, I'm sure you heard of, but there are a couple different definitions of those that we'll go into in more detail. And then we'll wrap up Chapter 7 with a discussion of oxidation-reduction reactions, of which the most common one you're familiar with is probably burning, combustion reactions. I put this slide in because I just think it's awesome, an awesome reference. So you may actually want to print it out or just kind of bookmark it till later. I'm not going to really spend time on it now, but it does show the different definitions of acid-base reactions, kind of gives you an overview of oxidation-reduction reactions, and then, of course, the double replacement or precipitation reactions. So it gives you kind of a figurative look at them. And what's kind of cool, too, acid-base reactions, at least the first couple we're going to talk about, involve transfer of a proton. Oxidation-reduction reactions involve transfer of an electron. And precipitation reactions are actually ions, cations, anions transferring. All right, so the three types of acid-base reactions we're going to talk about are shown here. Arrhenius was the original definition of an acid-base reaction, and it was limited to reactions that took place in water and involve production of either a hydrogen ion or a hydroxide ion. Then a little bit more encompassing after that came along the Bronsted-Lowry definition of acid-base reactions, which included more substances. And Bronsted-Lowry said it doesn't have to occur in water, that you can have an acid-base reaction outside of water. And it didn't have to, the main difference was in the classification of a Bronsted-Lowry base. It said the base did not have to produce hydroxide, that it just had to have a lone pair of electrons on it. And finally, the most recent and most broad definition of acid-base reactions are Lewis acid-base reactions. And the definition is different, but if you think about it a certain way, it's really quite similar. But Lewis acid-base are described in terms of being either a lone pair of electron donor or a lone pair of electron acceptor. And depending on which, it's classified as an acid or a base. All right, so we're going to start with the Arrhenius, the oldest model, first. And as I said before, the theory, that original theory defined an acid as something that produced hydronium ion in aqueous solution. That's actually what we measure with pH papers, that hydronium ion. That's how we measure how acidic something is. The Arrhenius theory defined a base as something that produced hydroxide ion. So if you're not familiar with the names of these ions, that's probably the first thing you need to do, okay, is learn what a hydronium and hydroxide. Some of you are tending to leave charges off of ions, so it's very, very important when you draw an ion that you also include the charge. Alrighty, just a brief side note about the hydrogen ion. A lot of acid-base reactions in textbooks or whatever will show the hydronium ion as the acid portion, and others will just have the hydrogen ion. What the heck's going on? Which one's right? Well, it turns out that chemists consider these two items equivalent to one another. So a hydrogen ion is simply kind of a shorthand way, whoops, because if you think about hydrogen ion surrounded by water molecules, what it quickly forms is the hydronium ion. So I've always thought of a hydronium ion as simply being a hydrogen ion riding on the back of a water molecule. But anyway, I mainly want you to remember that these two are considered to be equivalent to a chemist. Also, a hydrogen ion is simply a hydrogen atom, which I'm not sure if you remember, a hydrogen atom has one proton in the nucleus and only one electron, okay? So if you take away the electron, which is what you do to make the hydrogen ion, what do you have left? Okay, all you have left when you take away that electron is one proton, okay? And so you will often see the hydrogen ion described as simply a proton. So this is just vocabulary to get used to, okay? Sometimes you're going to see H3O plus, sometimes just H plus, sometimes just the word proton, and they are all considered equivalent. All right. There are two major classifications of acids. There are strong acids and there are weak acids. Strong acids are much easier to deal with, so we're going to start with those. A strong acid is simply defined as an acid that completely ionizes in solution. So, for example, hydrochloric acid is a strong acid. When you put it in water, it completely ionizes 100%, so that there is none of the original intact acid left, okay? That is a definition of a strong acid. So if I asked you to look at these two diagrams and label which one was a strong acid and which one was a weak acid, which one would you choose? Well, let's say that this is an intact acid, all right? So let's say it's HCl. So the little one would be hydrogen, the big one would be chlorine. So this would be an intact acid, not ionized, okay? Now look at this image here. All of the original acid is now completely in separate ionic form. So this is a strong acid. On the other hand, a weak acid, I'm not sure if you've heard of acetic acid. That's what's in vinegar. But acetic acid is a weak acid. And the definition of a weak acid is it's an acid, so it's going to form some ions, okay? But not completely, okay? So there's going to be a considerable amount of the original intact acid left. So whereas there was 0 of the intact strong acid left, there might be as much as like 99% of the original intact acid if you're dealing with a weak acid. So this second image represents a weak acid because you can see that there are still quite a few of the original intact acid molecules and only a few of the individual ions. Okay. All right, so how do we handle writing a chemical equation for a weak acid and a strong acid? So again, we're going to start with a strong acid. The first thing you need to be able to do first, though, is to write out a balanced equation. Let me move this over. There we go. Write out a balanced equation for an acid-base reaction, okay? So that if I gave you just the reactants and said, okay, what are the products? You need to be able to write what they are. So the products of a strong acid reacting with a strong base, water is always one of the products, okay? And then the salt, or an ionic compound, is the other product. So after you make water, that's combining the hydrogen ion from the acid and the hydroxide from the base. What's left over you're going to combine, and what's left over in this case is NaCl. Remember to put the metal first. That's just convention. In other words, don't write it as ClNa. That's not right. All right, so once you can write that balanced, what we call molecular equation, so you haven't shown anything as an ion, you've just kind of given an overall view of what's going on chemically. If you are asked to write the total ionic equation, they are asking you to separate or ionize or break apart those compounds that exist as ionized in solution. So from the definition I just gave you on the last slide, if you have a strong acid or a strong base, that means in solution they exist 100% as the individual separated ions. So HCl truly exists in water as hydrogen ion and separate from it chloride ion. Sodium hydroxide is a strong base, so it exists in solution 100% as separate sodium ions and hydroxide ions. Make sure you know all those charges. Water, as well as all covalent compounds, do not ionize, okay? Do not ionize, do not break apart. So you must leave covalent compounds intact. All right. Then we know that most ionic compounds are soluble in water. And what do ionic compounds do when they dissolve? They break apart into the individual ions. All right, so this is the total ionic equation. Then we have something called the net ionic equation. And what that is you look at your total ionic equation and you cross out the ions that are the same on both sides of the equation. Okay, so we have sodium ion on both sides, we have chloride ion on both sides. And then you rewrite what's left, what hasn't been crossed out. And in this case, we're making water. And that's why acid-base reactions are called neutralization reactions, because you're turning an acid and base that could burn you, each one of them could burn you, and you're turning them into water. So they're neutralizing each other. Anyway, when you rewrite the total ionic equation, leaving out the things that have been crossed out, that is your net ionic equation. The net ionic tells you what has actually chemically reacted, okay? The others are called, the things that got crossed out are called spectator ions. All right, so some people just kind of tend to like a list of rules or guidelines. And so here are the guidelines for writing a net ionic, which will be important in this unit. The first thing, you always want to write a balanced molecular equation, chemical equation, like we did first. You have to know what to separate into ions and what to leave intact, okay? Strong acids and bases, and all ionic compounds that are just soluble in water get split up into individual ions. Any type of covalent compounds, as well as weak acids and bases, are left intact. Okay, they don't separate into ions. Then working towards your net ionic equation, make sure you cross out the spectator ions. If every now and then, and it's usually somebody trying to trick you, you will cancel out everything in the entire total ionic equation. If that happens, that means there's no chemical reaction overall. All right, and that's it. Here is one to practice. I would suggest pausing the video at this point and seeing if you can write the products from this reaction. It's a typical acid-base reaction. Okay, see if you can write the products. Well, as I told you, one of the products will always be water. And what do you have left? Okay, you have the potassium combining with the NO3. That's a polyatomic ion called nitrate, if you remember. Always write the metal first in a chemical formula. That's just convention. Okay, so that is our balanced molecular equation. What's the total ionic equation? All right, one by one, we have to decide what to separate and what not. So I happen to know that nitric acid is a strong acid, and so it's separated. You're going to have to, in this unit, there's quite a bit of memorization. You're going to have to memorize which acids and bases are strong, so you know which to separate, and you're going to have to memorize which ionic compounds are soluble, because it's only soluble ionic compounds that get ionized in the total ionic equation. So H plus NO3, because it's a strong acid. KOH is also a strong base. All right, now we go to the product side. Potassium nitrate happens to be a soluble ionic compound. You must know the charges. Okay, so if you need help reviewing what common charges are, you can Google it. You can go to my YouTube channel and listen to a lecture, or you can come and ask me or one of our teaching assistants. Okay, water, always leave intact. It doesn't contain any ions to begin with. And there you go. So now we are going to cross out the spectator ions. So there's potassium ion on both sides, and there's nitrate ion on both sides. And look what we're left with. Okay, so I'm going to tell you right now, and I would jot it down, commit it to memory for a test. Whenever you react a strong acid and a strong base, they both have to be strong, the net ionic equation will always be this, production of water. Alrighty, onward to the more modern definition of acids and bases. It's also more general, more encompassing, and includes more substances. So the definition of the acid is very similar. The Bronsted-Lowry says an acid is a proton donor. Remember, a proton's just hydrogen ion. So in an Arrhenius acid, yeah, and so many words said about the same thing. What's different is the definition for a base. Okay, so whereas the Arrhenius definition said a base had to produce hydroxide in solution, the Bronsted-Lowry definition doesn't say any such thing. It just says the base has to be a proton acceptor. So it has to be something that has a lone pair of electrons, because those lone pair of electrons are going to be used to make a bond with the hydrogen ion. So let's look at an example here. Okay, nitrogen, and we're going to revisit Lewis structures. You're going to have to relearn how to draw Lewis structures. So this is ammonia. Nitrogen has a lone pair of electrons, and water, you will find out, can serve as an acid or a base. In this reaction, it's serving as an acid. Now, could you look at this reaction, if it wasn't labeled already, and tell me what was acting as an acid and what was acting as a base? That's an important skill. How can you tell? Well, look at each reactant and see what it turns into. NH3 turns into NH4. How did it do that? What happened to it? Well, it accepted a proton or hydrogen ion, right? To go from NH3 to NH4+. So that, by definition, makes it the base. Now let's look at, let's look at water. Water goes from H2O to hydroxide. What has happened? It has given up or lost a hydrogen ion, okay, which means by definition it's acted as an acid. So again, you need to be able to label all of those, and then that helps you predict products too. But again, because the nitrogen has a lone pair of electrons, that lone pair of electrons can be used to make a bond with a hydrogen ion. All right, a little bit more vocabulary. And this is going to seem really easy, but I'm here to tell you the majority of students, even though it seems easy now, get really jumbled up over this. So make a note to yourself for sure that when you're done listening to this lecture, you go to the practice problems, and there's one on identifying conjugate acid-base pairs. So what this slide is focusing on, after you've identified the acid and the base, there's something called conjugate acid and conjugate base you need to be able to determine. And it's not hard, really. Let's look at the acid first. Whatever the acid turns into, okay, so you start with HCl. What do acids do? They give away a proton. What's left when it does? What's left is Cl minus, okay? So what's left? Okay, after H plus is given away. All right, so you just take away a hydrogen atom from the acid. Whatever's left is called the conjugate base. Okay, so notice it started as an acid and it ended as a base. So acid always goes with base, base always goes with acid. All right, so now let's look at the base. Water is serving as the base here because it's accepting the proton from HCl. So what does the base turn into? When water accepts a proton, it becomes H3O. So what started as a base will end up as a conjugate acid. So again, please practice a bunch of those. All right, let's try a couple simple ones. Water can serve as an acid or a base, so it can get tricky. It depends what it's in the presence of. So what is the conjugate acid of water? Put the video on pause and see if you can figure that out. It's a little bit tricky. Well, I'm going to tell you how I think through this. I'm like, okay, if it's asking me for the conjugate acid, then how did this begin? It began as a base. If it makes a conjugate acid, that means it started as a base. All right? So if water is serving as a base, what does a base do? A base accepts a proton, right? That's the definition of a base. All right. What is formed when this accepts a proton? Oh, we get the H3O plus. So this answers the question. This is the conjugate acid of water. Let's try it the other way. Alrighty. If they're asking you for the conjugate base, that means that the substance started as an acid. Okay, what do acids do? They donate protons. All right. So now look back at the substance they give you. Have it act as an acid. In other words, have it donate a proton. And what's left when it donates a proton? Hydroxide is what's left. Okay? So since it started as an acid, what it makes is the conjugate base. Here's some more to practice. And this is probably the most challenging part of this PowerPoint because you have to know how to identify the conjugate pairs, but you also have to remember how to draw a Lewis structure. So my guess is, just from knowing most of y'all, that you're really rusty on drawing Lewis structures, and so you really may want to go to my YouTube channel, and what you would do if you haven't seen it yet is just Google my name, Lori Maffei, YouTube, and I have at least one lecture in there on Lewis structures, if not more. All right, so again, try to put this on pause and see if you can get these yourself. I'm going to go through them kind of quickly. If it's asking for conjugate acid, that means that these materials started as bases. Okay, so if we want the conjugate acid of water, started as a base, which means it accepts a proton. Okay, so bases accept protons, and when it does so, it becomes this. All right, so this is the conjugate acid. I'm going to use Ca from now on, okay? And NH3. When NH3 acts as a base, in other words, when it accepts a proton, it becomes NH4 plus, okay? So that's the conjugate acid of NH3. CH3OH. Okay, when it serves as a base, which means when it accepts a hydrogen ion, it becomes CH3OH2 plus charge. Notice that whenever you accept a hydrogen ion, you also gain a positive charge, okay? All right, so those are all the conjugate acids of these three. How about the second part of the question? What's the conjugate base of each? Okay, if they're asking for a conjugate base, that means it started as an acid. What do acids do? They donate a hydrogen ion. Okay, so when water donates hydrogen ion, what's left? Hydroxide. So that would be the conjugate base of water. Let's do it for ammonia, NH3. Again, when NH3 acts as an acid, that means it donates a hydrogen ion, which means it'd be NH2 minus. So again, notice whenever you give away or donate a hydrogen ion, because you took an H plus away, you're left with a negative sign. And finally, CH3OH, when it acts, well, it starts as an acid, which means it donates a proton. What would then be left over is this. So that would be the conjugate base of CH3OH. Now, I'm going to take a short little jaunt into drawing Lewis structures. So you can skip over this if you're an expert already. So let's start really easy. Let's say I told you to draw the Lewis structure of water. Let me go through the quick rules. Rule 1 would be count total number of valence electrons. Okay, so you have to remember how many valence electrons are in each element. So if you look at the periodic table, the number of valence electrons matches the group or the family number, the column. So the group 1A has 1 valence. Group 2A has 2 valence. Then you skip over to the aluminum group that has 3 valence. The carbon group has 4. The nitrogen group has 5. Oxygen group has 6. And fluorine group has 7. And the noble gases, like helium is the first one, have 8. Well, helium has 2, so because it's weird. But let's go down to neon. The rest of the noble gases have 8 valence. Anyway, so the total valence electrons in water, each hydrogen has 1 valence electrons because it's in group 1A. Oxygen has 6 valence electrons. So that's a total of 8 valence electrons for water. Okay? So the second step is draw single bonds between all atoms. Draw single bonds between atoms. Okay? So, and now remember, each single bond contains 2 electrons. So we have used a total of 4 electrons so far. You got to find a home for all of the valence electrons. So we have 4 more valence electrons we have to find a home for. Well, hydrogen, if you have forgotten, can only hold a maximum of 2 electrons, okay? So, and each of them already have 2 electrons from this bond, the 2 electrons in the bond that they're sharing. So that means that leftover electrons, after the outer atoms have an octet, extra leftover electrons go in the central atom. Okay, so I just put 2 pairs of electrons, or a total of 4 electrons on the oxygen. Okay, so I would strongly recommend practicing drawing Lewis structures some more, because this is a really, really simple one. All right, one of the things about the CLUE curriculum is we talk about intermolecular forces a ton, and we explain how atoms interact with each other in a chemical reaction, which is going to help you a lot in future chemistry courses. So remember, first of all, that this dotted or dashed line represents an intermolecular force. So here's hydrochloric acid, HCl, and here's water. And this is showing the intermolecular force between them. So the more electronegative atoms in both compounds will have a partial negative charge over them, and the less electronegative atoms have a partial positive charge. So we know opposite charges attract. So we're going to put this electropositive hydrogen next to the electronegative oxygen on the water molecule. They're going to be attracted to each other, therefore the dotted or dashed line. Now in an acid and base reaction, this strong intermolecular attraction turns out that this electronegative oxygen is actually like pulling and tugging on this hydrogen ion. It wants it. And so the hydrogen-chlorine bond starts weakening. And if the oxygen over from water pulls hard enough, this bond is going to break, and look what you've got. Okay? So this is an acid-base reaction, and that's what we call showing the mechanism of it, the method by which these products are formed. And just kind of remind you, we're going to be talking a lot about intermolecular forces, so remember how to identify. This one is a dipole-dipole, the strongest one, because chlorine is not one of the electronegative atoms that can hydrogen bond. So this is really just showing the same thing, okay? Again, the stronger the intermolecular force gets, the weaker the covalent bond between hydrogen and chlorine gets. All right, so let's just do a little bit more practicing. See if you can identify not only the acid, but the acid, the base, the conjugate acid, and the conjugate base. So turn off the video, see if you can do that. How I would approach it was I would look at each reactant and say, okay, what happened to it? All right, let's see, what happened to it? Oh, it gained a hydrogen ion. So if something accepts or gains a hydrogen ion, what is it? It's a base. All right, that means I'm going to expect the water to be an acid, but I'm going to check and make sure. So what happens to the water? Yep, just as I expected, water donated a hydrogen ion, okay? And so it is serving as the acid. Now remember, whatever the substance turns into is the conjugate pair. So whatever started as the acid ends as the conjugate base. Similarly, whatever started as the base ends with the conjugate acid. All righty, almost done. All right, this is showing a mechanism again, and we'll be doing a lot of those this semester. Okay, so again, you want to start out by showing the attraction between the base, the electron acceptor, and water is the acid in this case. So the electronegative atom on the base with its lone pair of electrons is going to be strongly attracted to the hydrogen ion on the acid. And as the nitrogen in this case pulls harder and harder on the hydrogen ion, the bond between the hydrogen and oxygen and water is going to start to loosen and get weaker until it breaks. And here are your products. All right, we're going to introduce arrows now. So there's one important rule I want you to remember. There will be more down the line, is that arrows are used to show the mechanism of a chemical reaction, and they always, this is the most important rule, start at a lone pair of electrons, a non-bonding pair of electrons, and go to or point to an electron deficient atom. Okay, electron deficient. What do I mean by electron deficient? Well, that's something that would have a partial positive charge. So if I told you to write the partial charges on hydrochloric acid, you know that chlorine's more electronegative than hydrogen, right? So it would get the partial negative. Hydrogen would get the partial positive. So if I said use mechanism arrows to show what happens when water reacts with hydrochloric acid, you would start at the lone pair, and you would, your arrow, and you would then point to the atom that's electropositive or has a partial positive, or in some cases full positive charge. And guess what? Now this is really important, so pay attention. This arrow shows you exactly where a new chemical bond is going to form. Okay? So let me draw that out in a little more detail. All right. So this lone pair of electrons is going to form a bond with this hydrogen ion. So look what we make then. You end up with H3O, the hydronium ion, right? And then this bond broke between hydrogen and chlorine, so you get chloride ion. Alrighty, same thing on the bottom here. You are starting with, it's always the base. If it's an acid-base reaction, you're always starting, arrow starts at the base, because that's the substance that always has a lone pair of electrons. So the arrow is going to point to the electropositive, which in an acid-base reaction is typically going to be a hydrogen ion. What is this second arrow doing? So I want you to remember the arrows represent bonds breaking and bonds forming. So this first arrow is showing the bond that's being formed between NH3 and hydrogen to make NH4. And the second arrow is showing that this bond between oxygen and hydrogen is breaking. And the two electrons that were in this bond are now going to move on to oxygen. So now you see the oxygen started with 2 lone pairs of electrons, and now you have 3 because you broke that bond and those 2 electrons went to oxygen. All right, we're almost done. 2 more slides. All right, so let's look at 2 water molecules. Okay, we're going to start getting into pH, and this kind of sets the stage for that. Water molecules can hydrogen bond with each other, okay? And so this just shows the diagram for hydrogen bonding of 2 water molecules. And the orientation's important. So the hydrogen bonding is going to be from the oxygen on one water molecule to the hydrogen on another because of the opposite partial charges. It turns out that even in pure water, you're going to get a small percentage, small but measurable percentage of the ions of water. Okay, so if I were to write this in just kind of formula, I would say H2O plus H2O gives OH plus H3O. Okay, that's what this is showing. That's called the autoionization of water. So in a sample water, I can't remember how much of that, it's like, oh yeah, I do. That was silly of me. It's 1 times 10 to the minus 14 molar. So not very much, but you can measure it. So it's important to remember that water can serve as either a base and accept a proton to make H3O, or it can serve as an acid and donate a proton to make hydroxide. And because that's possible, even pure water can autoionize and make those ions. So let's finish up with this. This might look a little trickier to you. So again, pause the video. Just give it a shot, even if you're not confident at all, okay? And then I will go through it. All right, well, hopefully by now you realize that HCl is an acid. So that's pretty easy, which means that this nitrogen-containing compound must be the base. So I'm going to give you another little hint, though. Anytime you see a nitrogen-based compound, almost always a weak base. Almost always. So just kind of tuck that back in your knowledge. All right, so what do bases do? Bases, the lone pair on the base is attracted to and attacks the hydrogen ion on the acid. So now let's draw that same compound, but let's draw with the hydrogen ion that it just attacked. Keep everything else the same, but remember, when you gain a hydrogen ion, you get a positive charge. All right, the acid is going to give up the hydrogen ion, so what's left? Okay, chloride. And you don't always have to draw the lone pairs, but you should for a while till you're comfortable. So notice that over here, chlorine had 3 lone pairs. But remember, when this bond breaks, the 2 electrons that were in the bond go on to the electronegative atom. So that's it. Conjugate pairs, let's go ahead and do that real quickly. So let's see, whatever the base becomes, so that'd be this guy, is the conjugate acid, and whatever the acid becomes is the conjugate base. Alrighty, that's it.